This is the 40th lecture of this course. Recall that given a 2 by 2 real matrix, its determinant can be interpreted geometrically as the signed area of the parallelogram spanned by the column vectors of that matrix. With that geometric intuition, motivation, we would like to define the determinant of square matrices of any order. In fact, more generally, we let V be a vector space of dimension n and fix an ordered basis un to en of V. We want to define the determinant as a function from the n-fold Cartesian product of V to F having these three properties. In the last lecture, we have seen that if there is a function with these three properties, then this following five facts must hold for that function. But however, we do not know so far whether there is any function at all with these three properties. In this lecture, we will show that we have such a function with the property, with the desired properties. So for that, we need to make a few definitions first. The first definition goes as follows. Given vector spaces V1, V2, Vk and W over the same field F, a function from the Cartesian product of V1, V2, Vk to W is said to be K-linear if, so before telling you the formal definition, let me first convey the idea. So earlier we have seen linear maps. So K-linear maps are nothing but you can regard them as an extension of that notion. So what is happening here, given a function from V1, the Cartesian product of V1, V2, Vk to W, one can regard this as a function with k vector variables. So k linear means if you for any I, if you freeze all variables other than the ith one, then the single variable function is linear. Okay, so the formal definition goes as follows. For any I, for any v1, v2, vi minus 1, vi plus 1 to vk, the map x goes to f of v1, v2, vi minus 1, x vi plus 1 vn is linear. Note that here, note that in this function, v1 to v minus 1 and vi plus 1 and to vn, all they are fixed. Okay, so this is, you can regard it as a single vector variable function, and this we insist to be linear. So for each I, if that happens, then we will call the map a K-linear map. Let me give you some examples so that it will the notion of a K-linear map will be clear to you at once. So if K is 1, that is we have one vector space, let's say V1 and W, then a one linear map is the same as a linear map. That's evident. So we should rather look for the maps where K is greater or equal to 2. So if K is 2, then those maps are called bilinear. So this is an example of a bilinear map. This is perhaps the simplest example. So a pair x comma y goes to xy, the usual product. So you can easily see if you freeze y, then x goes to xy is a one variable function of x, which is linear. So this is one example. The second example is basically the determinant of a 2 by 2 matrix over any f. So for convenience, here we will write the members of f2 as a column vector instead of writing them as pairs. So given a pair of column vectors, we map it to AD minus BC. It's easy to see that if you freeze either this second component of this ordered pair, then AB goes to AD minus BC is a linear map from F2 to F. Okay, and more generally, so this is the determinant map for 2 by 2 matrix. More generally, the determinant function which we wish to define, which we wish to construct, so that is a function with these three properties. The determinant function which we wish to construct, though we don't know whether it exists or not, but if exists, then that function will be a n-linear map. Why so? So for that we look at this property 2, which takes care of the scalar property 2. Just a minute. Sorry. We look at property 2 and this and the fourth one. Okay, and this fourth one. So property 2 takes care about the scalar multiplication, and this one takes care about the addition, vector addition. Okay. The next definition that we are going to make is a permutation on a set. So let X be a non-empty set. By a permutation of X, I mean a 1, 1 and onto map on X. Okay, so by definition, every permutation is a bijective map on X. Let me give you an example. So suppose my set is 1 up to 5, and we consider this map. The 1 goes to 3, 2 goes to 5, 3 goes to 4, 4 goes to 2, and 5 goes to 1. It is a permutation on the set 1 up to 5. So we will fix a notation here. If X becomes 1 up to n for any natural number m, then the collection of all permutations of this X will be denoted by Sn. Let me just add the word permutations of X is denoted by Sn. So here we have a example of a permutation in S5. So for permutations, we will it's customary to use a very special notation. So instead of writing like this, of course we can write it. This is a very general notation. Instead of writing this, we would simply use this array notations. It is an array. So on the top row we will write 1 up to n, and in the bottom row we will write the corresponding images. So for every I on the top row, just below that we will write its image. So this permutation of 1 up to 5 thus written in this notation like this. Okay, so 1 3 2 5 3 4 4 2 5 1. There is something very interesting to be noted here. So you see the way these elements are being moved by the permutation, that is somewhat so 1 is going to 3, then 3 is going to 4, 4 is going to 2, right? And then 2 is going to 5, and 5 is 1. So basically what it is doing is it is permuting these elements in the cyclic manner. So therefore it's legitimate to call such permutations as the cycles. All such permutations as cycles. The formal definition is as follows: that given sigma in Sn is said to be a cycle if there exist elements A1 to A are all distinct, such that these elements are being moved cyclically among themselves in this order, in the order of their indexes, and everything else is fixed. So the pictorially we can visualize this as follows: A1 goes to A2, A2 goes to A3, and then A3 goes to A4, and thus finally A4 comes back to A1. So if sigma is a cycle, we will simplify the notation as follows. So observe that in order to know, for a cycle, what all we need to know is the elements which are moved. Okay, the elements which are fixed, they are not of much interest to us right now. In order to know the permutation, in order to know a permutation which is a cycle, we need to know the elements which are being moved and the order in which they are moved in the cyclic manner. Okay, so therefore in view of that we will use this notation. So so this notation means that each element here, each term here is being moved to the next term, and the last term comes back to the first term. So this is a legitimate, it is reasonable to use this notation, as we just need to know the elements and the succession in which they are being moved. Okay, now we make a further definition that two cycles are said to be disjoint if two cycles, let's say one to AR and B1 B2 BL, are said to be disjoint if no AI is equal to any BJ, or in other words, the set the sets AN to AR and B1 B2 BL, these sets are disjoint. Okay, so if two sets, their intersection is empty, we call those sets as disjoint. If therefore, if for a permutation if for two cycles the corresponding sets are disjoint, we will call these permutations are disjoint. One thing to note regarding to disjoint permutation, disjoint cycles is disjoint cycles always commute. So that's a very easy to see, since this one only moves BJs, this one only moves BJs, and and all the BJs are left fixed by this permutation, and similarly this one moves AIs, and all AIs are left fixed by BJs. So basically it's up to you that whether you will permute the AIs first or permute the BJs first. So this is indeed an expected one. Okay, so now let's come to the main theorem. So let me first explain. So first we define permutation of a set X, and in particular specialize that to 1 up to n. Then we define the cycles. Now we are going to see that the cycles play the role of building blocks. The cycles play a fundamental role in the permutations. Permutations in the following sense, that given any permutation, there exist cycles tau 1 up to tau L, such that any tau I and tau j, for any pair tau and tau j, they will be disjoint. So given a permutation sigma, there exist pairwise disjoint cycles such that sigma can be written as a product of them. So therefore what we have seen is every permutation is a since I have used a different word, I should say a few words regarding that. So it is, when dealing with permutations, more precisely Sn, so it is customary to speak the word product in the place of composition. So again, let me explain what I mean. So given two permutations sigma and tau, it's legitimate to talk about sigma compose tau, right? But in this very special situation, where sigma tau, they are lying they are all members in some Sn. So instead of saying composition, we will rather say product. Please do not confuse that with the notion of product that you are familiar with. So here product means transpositions. So this theorem, what it tells is every cycle, every permutation is a product of disjoint cycles. Okay, every permutation is a product of disjoint cycles. This is what this theorem says. The proof of this theorem is quite elementary. So first what we will do is we will start with an X, and we will see that where X can be moved by the repeated use of sigma. So X, sigma square X, and so on. So this is a subset of 1 up to n. So therefore this set cannot be infinite. In particular, since this set is a finite, so in particular we have m and m dash different such that they are different, and but sigma to the power mx and sigma to the power m prime x, they are the same. Okay. So this from this we get there is a positive integer. There is a positive integer m naught, such that sigma to the power m naught x equals to x. It's very easy to see. For example, if m is bigger than m prime, so apply both sides sigma to the power m minus m prime. That will then m minus m prime will be the choice of m naught. So similarly, if m prime is bigger than m, you multiply both sides by sigma to the power m prime minus m. However, in either case, we have a natural number. M naught, such that sigma to the power m naught equals to x. So, well, it may so happen that sigma for a positive integer less than m naught, for a positive integer m1 less than m naught, sigma to the power m1 x might be equal to x. It may so happen. So what we will do is we will choose k to be the least positive integer such that this happens. So the reason for choosing the least one is because if once we have chosen the least positive integer k, then for that k we can ensure that this collection of points in 1 up to n, ax sigma is up to sigma to the power k minus 1x, they are all distinct. It's easy to see if two terms are equal, then we will have a situation like this, and that leads me to a positive integer less than k, such that sigma raised to the power that positive integer applied on x will be x. That contradicts that challenges the minimality. Challenges the minimality of k. Okay, so exactly similar argument. So once we have obtained that these are all distinct, we will consider tau 1 to be this cycle. So what is tau 1 doing? Tau 1 is permuting these elements exactly in the way sigma permutes them, and tau 1 leaves everything else fixed. So if these are all the elements in 1 up to n, then we will stop. Okay. And immediately, if that is the case, immediately we see that the sigma becomes the cycle. If not, then what we will do is we will pick an y outside this set, and then look for and apply the same process. So here we make sure that none of these elements here lie here. So that's an easy observation. If some sigma to the power ry equal to sigma to the power, let's say this, then that implies that y is some power of sigma. So y is some let's say sigma to, if this happens, then from which we immediately get y is some, let's say, sigma to the power k prime x, which contradicts the choice of y. So for this collection we argue previously, and that leads me to a tau 2. So what is tau 2? Let me again write for you. This is then got y sigma y, and till the point it goes up to the point when they are all distinct, and then after that things will be repeating. Now therefore this tau 1 and tau 2 that we have obtained, they must be disjoint, which is clear from this observation. So if this list together with that list, if this list and together with that list, if they exhaust 1 up to n, then we will stop. In that case we do have tau 1 compose tau 2. Otherwise we will pick up. So if their union does not exhaust 1 up to n, so then we will pick something. We will pick something from this and go ahead. So since we are only having n elements, at some point of time we have to stop. So that that leads me to, if we stop after L steps, so therefore we get permutation tau 1 up to tau 1, tau 2, tau L, and any two such different tau i's are disjoint, and sigma is their product. Okay. Thus, we have proved that any sigma is the product of disjoint cycles. Here we will adopt a convention that so whenever we are writing sigma is a product of disjoint cycles, we will omit the one cycle. So what is a one cycle? A one cycle is necessarily a fixed point. In fact, and one cycle is nothing but a fixed point, nothing but is equivalent to having that point fixed. Okay. So as I say that for the points which are fixed, these are, I mean, we will rather focus, we will rather put our focus on the points which are being moved. Okay. So therefore, it's customary to omit the one cycles from from the one cycles from the notation, while writing permutation as a product of disjoint cycles. Okay, so let me So thus from now we assume that whenever we write sigma is whenever we say that sigma is the product of this disjoint cycles tau 1 up to tau L, so each cycle must have length L. It must have length 2. So again, let me remind you, for a cycle, if sigma is a cycle, then this R is called as the length of we will say R is the length of sigma. All right. So fine. So now we will talk about the cycles of length 2. These are called transpositions. For example, 1, 2, 3, 4. These are transpositions. So now what we will observe that any cycle is a product of transpositions, but certainly we don't have pairwise disjointness here. Okay, also we will add up for one more notation, that since we have said that here we will rather call the composition as the product, so we will drop just a minute. So we'll rather drop this notation for composition from the notation and simply write it like this, so that it indeed looks like a product. But again, you should not be forgetful that here the product means composition. This is just to simplify the notation, and it's customary to say product in terms of say product in the place of composition here. Okay, so in view of this observation, what we get is the following, that earlier, just a minute. Earlier we have proved that any permutation is the product of disjoint cycles. Now each cycle is a product of transpositions. Therefore, putting these two facts together, we see that every permutation is a product of transpositions. But remember, here we cannot insist that those transpositions, if we pick any two different transpositions, they will be always disjoint. That we cannot insist. So let me, as an example, let me show you how this permutation can be written as a product of disjoint, can be written as a product of disjoint cycles first, and then how it becomes the product of transpositions. So first we see that if you remember the way we given any sigma, we write it as a product of transpositions. So product of given a permutation, how we write it as a product of cycles. So you see, if we use that technique, you see, we first start with 1 goes to 3, then 3 goes to 2, then 2 goes back to 4, and 4 is 1. So therefore this is a cycle. and then for beyond 1 2 3 4 we pick up 5. So 5 6 and 6 comes up 5, and then we have 7. 7 is one cycle because it's a fixed point, so we will simply omit 7 in the omit 7 as we have already agreed to adopt. Now we look for 8 and 9. So thus this is the cycle decomposition of this permutation. Now we have already we have 5 6 and 8 9 already we have these two transpositions. So it only requires to write this as a product of transpositions, and this is usually this, okay, using from in view of this observation. So therefore thus this permutation becomes the product of these transpositions, okay. Now I would like to draw your attention to a very interesting and important point, that this is the following, that given a permutation, the number of transpositions whose product is going to be the given permutation is not unique. For example, the same permutation can be written like this. So we have kept all the terms here, and with that we just added the same transposition 1 2 twice. The reason for that is, since 1 2 being a transposition is of order 2, it's a self-inverse. So the product of the rightmost rightmost two terms will be identity. So adding this transposition twice here, in that adding this transposition twice here does not make any change. So thus earlier it was written as a product of 5 transpositions. Now it is written as a product of 7 transpositions. We can keep on going like this. So the thing is, the number of transpositions whose product is going to be the given permutation is not unique. However, one thing that we can guess from this example is, or the way we were adding more and more transpositions here. From that, what we can guess is that so once it is written as a product of 5 transpositions, then if you want to write, let me again articulate that's better. So the number, as I said, is not unique. However, from this example, or more precisely the way we are adding more and more transpositions here, from that it is clear that though the number is not unique, but its parity has to be unique. So by a parity, I mean either it is to be odd or it is to be even. Okay. So in other words, if we write this as a product of 5 transpositions, then we can write it as a product of 7 transpositions, 9 transpositions, 11 transpositions. But however, we cannot write it as a product of, let's say, even number of transpositions. Okay. That is what we can guess from the computations that we are making. In fact, this is the content of our next theorem, which is a very important theorem. Loosely speaking, it says that always even or always odd. So what it means is, given a permutation, the number of transpositions whose product is going to be that given permutation is either always even or always odd. So in other words, suppose I can write for example, this permutation we have written here we have up to this point we have written is as a product of 5 transpositions. So we cannot ever write this as a product of even number of transpositions. Okay. So therefore I again repeat that the number may not be unique, but its parity has to be unique. And that observation leads us to the following definitions of even permutation or odd permutation. Remember, if a transposition is written as the product of even number of transpositions, then it cannot be written as the product of odd number of transpositions. So therefore, in it's legitimate to call such transpositions as it's legitimate to call those permutations as the even permutations, and similarly we define odd permutations. Let me give you some example. So what is the product, an example of an even permutation is 1 2 3 4 in S4, and an odd permutation, the simplest example is simplest example is the transpositions. And another example of an even permutation is the identity, because it can be written as, let's say, 1 2 times 1 2. Okay, so once we have defined even and odd permutations, then we will define what we mean by the sign of a permutation. So given a permutation sigma, its sign is 1 if sigma is even, or -1 if it is odd. So thus identity sign of identity is 1, sign of a transposition is -1. So let's also note that sign is a multiplicative function. That is, if we have two permutation sigma and tau, then sign of sigma tau is the sign of sigma times sign of tau. So it's very easy to see that, let's say if sigma, if one of them is odd and another one is even, then the product is immediately written as product is immediately seen to be the product of odd number of transpositions. Therefore the sign on the left hand side will be -1. And now if you come here, since one of them is odd and another is even, so right hand side is also -1. Similarly for the other cases. And also from here it follows immediately that the sign of sigma is same as sign of sigma inverse, because sign of identity is 1, so sin sigma times sin sigma inverse, the product is 1. So therefore either both are +1 or both are -1. Okay, we will go ahead. Now for a map defined from the n-fold Cartesian product of V to F, we call the map to be a skew-symmetric if for every sigma, if we permute for every sigma and every V1 V to Vn, if we permute the Vi's according to sigma, and then so try to understand, since this is a function defined over the Cartesian product, so whenever we have n vectors, then we arrange it. We can arrange those vectors in a way, and then for that tuple we look at the value of f at that tuple. So it says that given v1 v2 vn, if we arrange, assume that initially these are ordered like this, that is v1 is the first vector, v2 is the second vector, and thus vn is the nth vector. If we now change this arrangement by sigma and then look at the values of f after that rearrangement, so this is nothing but the value of f for the original arrangement v1 v2 vn multiplied by an appropriate sign, namely the sign of the permutation. So let me give you an example. Let me give you an example. So we will look at the example of the 2 by 2 determinant. So a b and c d is a d minus bc. If you see that if we interchange these two, then that means we have that means our sigma here is the transposition 1 2. Then that will result, if we interchange these two, then the value of after interchanging it goes to just the minus of this. So here -1 is coming from the sign of the transposition 1 2. So so therefore this map is skew-symmetric. And more generally, the determinant function which we wish to define, if that exists, then that has to be skew-symmetric. Why? That's very easy. So if you start with any permutation, we know that can be written as a product of transpositions. So first what we will do is we will first, so for any v1, v2, vn, so first we will rearrange those vi's by tau k, and therefore at the level of value it will contribute a negative sign. Then after rearranging the terms by tau k, then we will further rearrange whatever we have using, whatever we have, we rearrange them further by tau k minus 1. Again that will contribute a minus 1. We keep on going like this. So finally, after performing k steps, we have arranged these elements according to sigma. And on the other hand, at every step we have got a minus 1. So therefore we have minus 1 to the power k of f, minus 1 to the power k of determinant v1, v2, vn. So now you see that the minus 1 to the power k is nothing but the sign of sigma. So therefore, if the determinant function exists, remember we have not proved that, we don't know whether such a function exists or not. If there is a function with the three properties that we have mentioned in the beginning, then that function has to be skew-symmetric. Now we come to the main theorem of this lecture. So far what we have checked is to understand that if there is a function, if there is a determinant function, then it must be n-linear skew-symmetric, it must be n-linear skew-symmetric. And also, if you remember to begin with, we have started with a basis, and this basis, and we want to insist that this has to be 1. So if you remember, this is nothing but this nothing but says that it is a unit of the measurement, because we want determinant to represent as the signed volume of the parallelogram. So therefore for that measurement we need a unit. So therefore we need a unit. That is, we have to specify parallelepiped whose volume we would like to consider 1. So that geometric requirement is reflected in the first property. Now we will now come to the main theorem. So in this theorem we will prove that given a vector space V of dimension n over f and the basis v1, e1, e2, en, there is a unique function which is n-linear skew-symmetric and having the value 1 on e1, e2, en. Let me again repeat earlier what we have proved, that if there is a determinant function, then it has to be n-linear skew-symmetric. And to begin with, we assume that it is taking the value 1 on the chosen ordered basis, on the fixed ordered basis e1, e2, en. Okay, but so if there is a determinant function, then these are to be held for that function, but we do not know whether such a function is there or not. This theorem indeed assures the existence and uniqueness of such a function. So it says that once we have fixed an ordered basis of a vector space of dimension n, we do have a function which is n-linear skew-symmetric and having the value 1 on e1, e2, en. All right. So now we will prove this theorem. So what do we need to what are we supposed to do in order to prove the theorem? We are supposed to construct an f satisfying these properties. Then we will show that that's the unique one. That is, if we have another function, with these three properties, then that function must be that one which we have constructed. Okay, so in order to construct f, let's try to first guess what it is going to be. Once we have made a reasonable guess, then we will proceed. Okay, so how will we guess? How does one guess? we will try to trace the function backwards from its properties. So we go as follows. Suppose we have chosen vectors v1, v2, vn and write vi as the linear combination of ei's. Then f of v1, v2, vn has to be this. Okay. So here what we do is we will write each of these terms in this shorthand notation. However, just to for our convenience, we will use different indices, different dummy indices for different components. So the first component, the indices is j1, where j1 is a runs from 1 to n. Similarly for j2 up to jn. Now since the function is n linear, that is, once we have frozen the second, third up to nth coordinate, it is going to be second up to nth component. Then it is going to be a linear map in the first component. Okay, so therefore we have f is the summation of a1 j1, where j1 runs 1 up to n of this. Then we look for any j1, we have this term. So here we are freezing the first component and third, fourth up to nth component. Okay. Now since from the n linearity we have that f is linear in the second component, that forces me to have this further split. Then we go on and go on. Finally we arrive at this place. So therefore, from the n linearity property of f, we see that f of v1, v2, vn must be this. Okay. Now let's try to see what this fellow is going to be. If we have, let's say, if the rth term here becomes equal to the kth term, where r not equal to k. So if two terms here, so for any j1, j2, jn, if two terms here, if two terms, or I should say that if two components here are equal, then this has to be 0, right? Because suppose jr is equal to jk, suppose jr is equal to jk for r not equal to k, then what we will do is we will interchange the rth and kth component, and that interchange will cause a minus sign. But however, since ej are equal to ejk, therefore this tuple is not going to change at all, right? So thus what we get is this quantity becomes the negative of itself, hence there it will be 0. So what we have seen is if any two ji's are equal, any two different ji's are equal, then such a term will vanish. So the only surviving terms in this sum, the only surviving summands in this sum are as follows. That only surviving terms in this summand, the only surviving summands in this sum are precisely those for which no jr is equal to jk for all k not equal to r. Okay. And what does that give us? What does that tell us? It tells us that since j1, j2, jn are n numbers from 1 up to n, and no two are equal, so therefore this shows that this map I goes to ji is indeed a permutation of 1 up to n. Let's denote that by sigma. Okay. So again try to understand that in this sum, the summands for which the summands which will survive are precisely those summands for which this assignment will be a permutation of 1 up to n. Therefore in this summand the number we have we have as many survivors as the number of as we have as many survivors as many permutations are there in Sn. Okay. Yeah, so the number of here the number of terms in this summand which are surviving, the number is same as that of elements in Sn. Okay, now let's observe further that if J1 to Jn, if I maps to Ji is a permutation, then if J1 up to Jn, once we denote this permutation by sigma, this is nothing but this. And now we are using the skew symmetry of F. So from the skew symmetry of F, we see that this is nothing but sine sigma times this and times F un to En. Further, we remember that the F which we would like to construct, that must have this property. So therefore, here this terms actually does not play any role. It becomes 1. Okay. So thus what we have seen is, if we have an F with these three properties, then the value of F for V1, V2, Vn must be the sum of this. Okay, that we now see, because every term becomes, so for only the terms that will survive, they correspond to the permutations, and therefore f of V1, V2, Vn will be the sum of these terms, where the sum runs over all permutations of 1 up to n. Now you see that in this description, there is no explicit reference of, there is no reference of F at all, in fact. So therefore, what it shows that whatever my F is, as long as it has the three properties, then its value at the point V1, V2, Vn has to be this, the sum of all such. It has to be this sum. So that indeed shows us, if such a F exists, then it has to be unique. Okay. So the uniqueness part is clear, and that is and it's independent of the existence part. Please try to follow what I am doing. We have shown that if there is an F with these three properties, then we see that the value of F for any V1, V2, Vn has to be the sum of these terms, and that shows us the uniqueness of F. And not only that, it also tells us how to construct F, because our primary job is to construct F. So with that motivation, we would now define F to be like F as follows. So for any V1, V2, Vn, we write Vi's as summation Ai's, Aij, Ej. Okay, we write summation Aij, Ej, and define F1, V2, Vn as this. Okay. Now it's our job to verify that it indeed satisfies the three properties. Again, try to understand what I am doing. We have shown if there is an F, then F has to be unique. Okay. So even up to this point, we don't know whether we do have such an F or not. We don't know. Even up to this point, we don't know whether we have any such F at all or not. With that, we don't know. But now we will show that we have one, and we define F to be like this. So now, in order to establish our claim that this F satisfies the required three properties, we will now verify the properties 1, 2, 3 one by one. So let's first do the third one. This is the most trivial one. So if V1, V2, Vn are just U1 to En, then we see that each ai sigma I for any sigma is nothing but delta I sigma I. Okay, because when V1 has only first coordinate 1 and rest are 0, similarly Vi has a ith coordinate 1 and rest are 0. Okay. So from this it follows that unless all sigma I is I, that term will not, unless all sigma I is I, the term will not survive, and for the only surviving term you will have is each of these will be 1, so the and sign of the identity permutation is also 1, so therefore you have 1. Now let's verify that the map is skew-symmetric. How does one prove the map is skew-symmetric? That's also quite easy. So we start with a tau in Sn. So let V1, V2, Vn, and we split each Vi as a linear combination of EIs as follows. So therefore now, therefore for any I, V sigma I is going to be this. So we'll relabel the coefficients for our convenience, because the way we have defined this f, that the way we have defined that description indeed depends upon the coefficients, with their indices. Okay, so therefore we will relabel the coefficients by different symbols. Let's bi, so that now we can directly. So once we have relabeled the v tau i's using this bij's, so let me again tell. So bij is defined as a tau ij. Okay. So for any ij, bij is defined a tau ij. So once we have relabeled the coefficient of bij, then we see that a v tau 1 up to v tau n becomes this fellow. Now we will put the values of write bij equal to a tau ij. So that gives me to this. Now let's observe that for any I, a tau I sigma I. So here, so a typical term in the product can be written like this: a tau I times sigma tau inverse of tau I, right? Now since I runs over all the elements of 1 up to n, then so is for tau I. Therefore we see that these terms, so these terms are nothing but, so they are nothing but these terms, perhaps arranged in a different manner, and at the level of product there won't be any change. So this product here is same as this product. Try to understand. We first observed that any such term can be written like this. So now as I runs over all elements in 1 up to n, therefore these terms are nothing but these terms, perhaps arranged in a different manner, but since we are taking the product, there it doesn't matter. Okay, now we make this obvious manipulation, because sigma tau inverse is sigma tau times the sign of sigma tau inverse is nothing but sine sigma into sine tau, because sine tau is sine tau inverse, and sine tau multiplied with sine tau will give us 1. Right, so we make this obvious manipulation. So once we have made this obvious manipulation, then we will make further observation that for any real valued function on Sn, so sum of all the values of phi, so this stands for the sum of all the values of phi, and that is easily seen to be this. So for any fixed tau, this sigma taus are nothing but, so if we fix a tau and then multiply each sigma by the tau, we are getting the same group elements. Okay, maybe arranged in a different way, but as we are taking sum, it doesn't matter. Okay, so this is now quite clear to us, and in view of this, we see that this sum is nothing but this sum. Okay, and what is this sum? This is our value of f1, v2, vn. So thus what we have seen is, for any tau, we obtain f tau 1 up to v tau 1 up to v tau n to be sine tau times f1, v2, vn. That shows that map is skew-symmetric. Now I would like to show the map is n linear. So in order to show the n linear property, in order to show the map is n-linear, I claim that it suffices to show the map is linear in the first variable. Okay, so why so? Suppose we have proved the map f is linear in the first variable. Now how to prove the map is linear in any other variable, let's say the ith variable. So what we will do is, so if we have vi plus vi prime in the ith variable, we first interchange the first variable and the ith variable, that will produce a minus sign. Now after interchanging the first variable, we have vi plus vi prime. There we will split that using the linearity, and then we further, so once it splits, there will be it will be the sum of two terms. For each such term, we will again interchange the ith and the first coordinate to bring vi or vi prime back to that ith coordinate, and since we are applying since we are interchanging the ith coordinate and the first coordinate here, so that will produce another negative sign, which basically cancels the earlier negative sign. Okay, and similarly we can argue for this for the scalar multiplication. So basically, in view of the skew-symmetry, we see that it suffices to prove the map is linear in the first variable. For that, what we do is, our technique will be just our technique is exactly same as what we have. Our technique is exactly similar to what we have done here. Okay. So we write vi as the linear combination of un into en, and do the same for v1 prime. Then v1 plus v1 prime will have this. So since our definition indeed depends upon the coefficients depends upon the coefficients together and with its indices. So for convenience, we will first relabel all the coefficients by this bij. So b11 up to b1n are precisely this, and for v2 up to and bkj equal to akj when k is bigger than 1. Okay. So thus now we see that f1 plus v1 prime v1 and v2 up to vn is nothing but this. Now we will substitute the values for bij. So for each sigma, the first term b1 sigma 1 will be this, and the second then the other terms will be same as those of so the on b1 sigma 1 will be, for that we need to put this, and for other terms we will simply those will be akjs. So therefore now we are allowed to split that into two parts. So this sum corresponds to the value of f1 v2 vn, and this indeed can be seen to be this from the definition. Okay, so thus we have checked that the function is thus we have changed we have proved that once we have frozen the components from 2 up to n, then the one variable function, namely the function in the first variable, preserves the vector addition. And similarly one can prove for the scalar multiplication. So as usual, we will write down the coefficients first and then relabel them. Then we will use the definition and then substitute the values for bij, and that will lead us to the desired one. So therefore we have finished the proof of the theorem. Okay, try to understand. So first we proved the uniqueness independent of the existence. once we have the and for to prove the existence, we first define f to be this. Then we verify the properties. Third property is trivial. Second property is also verified. And in view of the second property, namely the skew symmetry, we see that it's enough to prove it is linear in the first variable in order to show it is a n-linear map. Okay. So yeah, thus we are done with the theorem. Now let's make two definitions. Now let's make a definition here. So given u1 to en, the f which exists and unique that we have seen in view of this so the given u1 to en, the f which exists and is unique is called the determinant function relative to the ordered basis u1 to en. So we denote that by det. So how is that defined? Det v1 v2 vn is defined as this. Okay, remember we have proved this for any v1 v2 vn. If we send this to this quantity, then this assignment gives me this assignment is the function that satisfies the three properties, and it is the unique one, as we have proved. So so for any v1 v2 vn, we denote this quantity by this det v1 v2 vn. Okay, so here vi's are written like this. We will finish soon, but before that let's make an observation. So suppose we have a function n linear and skew symmetric. Then like earlier we have seen that the n-linearity and skew symmetry leads us up to this point, that is g of v1 v2 vn must be this together with g u1 to en. Remember this terminology has no this term is independent of sigma, hence we can take it out, and once we take it out, what is left here is the determinant was the value of the determinant of at the tuple v1 v2 vn related to the basis u1 to en. Okay, so therefore for any n-linear and skew-symmetric function, the value of any n-linear and skew-symmetric function is nothing but a scalar multiple of so any n-linear skew-symmetric map is necessarily a scalar multiple of the determinant map, and the converse is trivial. So therefore we have all the n-linear skew-symmetric maps. Okay, let me try to again explain. So once a fixed and ordered basis u1 to en, then every n-linear skew-symmetric map and then the n-linear and skew-symmetric maps are precisely the scalar multiples of the determinant map relative to the ordered basis u1 to en that we have fixed in the beginning. Okay, and the scalar is nothing but the value of the map at the point at the point u1 to en. Okay, fine. This observation will be used later on, maybe in the next lecture. Now we go ahead, we make a definition, and with that I will finish this lecture. So as we have said in the beginning that our aim is to define the notion of determinant for any square matrix of order n, where is n is any natural number. In general, so far what we have done is we have defined the determinant for any vector space V. For any vector space V, we have defined the determinant as a n-linear skew-symmetric map with a further normalization it's a map from the n-fold Cartesian product of V to F. That's what we have done up to this point. Now we will complete our aim of defining determinant for any square matrix. So we specialize this. So try to remember that we have proved anyway, given any vector space V of dimension n, and any fixed ordered basis, we have a determinant function relative to that. So we now specialize that to this situation: V equal to Fn, and the standard ordered basis of Fn. Then for this V and then standard ordered basis, we do have a determinant map that sends a tuple of vectors to this. Okay. Now we recall that, or we can easily see that this n-fold Cartesian product of Fn is nothing but isomorphic to, linearly isomorphic to the space of square matrices. How do we do it? It's very easy. So starting with a square matrix, so we regard all of its columns as the vectors in Fn. So therefore, given a square matrix, we map the square matrix to this tuple of vectors. So the ith component of this tuple is the ith column, which is a vector in Fn. Okay, and it's easy to say that this is a linear isomorphism. So this determinant map, that is specializing the general theorem to this case. So this determinant map composed with this linear isomorphism gives us the following map, where a square matrix is being sent to this. We define this quantity to be the determinant of the square matrix. So that's how the determinant of any square matrix is defined. Remember, the main point is the theorem. What is the theorem? The theorem is for any vector space given any fixed ordered basis, this is what we have. Specialize this theorem to that case, we get the determinant of any square matrix. In the next lecture, we will explore the basic properties for the determinant of matrices. And with that, we will finish this lecture. Thank you.